වෙනද?
හරි. මම මේ අයා මාරට නවත්තනවා මේ ක්ලාස් එකට යන්න තියෙන හින්දා. අපි ඊට පස්සේ මම ඔයාලට ආයෙ දවසක් මේ ලබන සතියේ ඉස්කෝලේ නිවාඩු දෙනවනේ. ඒක මම බලලා ඔයාලට දවස් දෙක තුනක් කරලා කරන්නම්. හරි. ඒ දවසේ. මොකද අපි ඔයාලට ෆ්‍රී වෙලා බලලා කරමු. රැ වුණත් අර කරේ මේ දවස් ටිකේ ඔයාලා ඉදක්කොට කරන්න බැරි නම් පොඩි මලකයක් වෙලා අපේ මහගෙදර ගියා මේ මලගෙදර ඉතින්. මේ last day we discussed about the black body radiation. Could I give the tutorial එකක් දුන්නා නේද මම? tutor දුන්නද නැද්ද?
tutor දුන්නා
නැද්ද? හරි. මම ඒක දාන්න. මේක දෙන්නම් ඔයාලට questions අර කරපු වගේ කරන්න පුළුවන්. අපි අද පාඩම ඩිස්කස් කරලා අපි photo electric effect එක ගන්න මේකේ last day we discussed about that the characteristic about this black body spectrum, right? I discussed that is the laws derived based on this observed experimental graph. There are so many laws they given that main two laws as Stefan law and Wien's displacement law we discussed, right? And then the scientists, there are many scientists, they went to explain about the shape of this graph theoretically, but they failed. The most closer explanations given by this Rayleigh gene and Wien X distribution. That's a Wien. We call that the Rayleigh gene and Wien law, Wien theory. They come close to this, close to explain about this experimentally observed spectrum, but they cannot, they couldn't explain the graph completely. The Rayleigh gene could able to explain about the one part of the graph, and Wien could able to explain the another part of the graph. By combining these two, the Max Planck completely explain about this graph, and he made a new theory about this because the people at the time they thinking about in classical mechanics. So that's Max Planck and Einstein showed that the classical mechanics are not suitable to explain this type of variations. So that new theory they build up. It's called the quantum mechanics. Right? So let's see how they explain this. Right? First to write there the Rayleigh genes theory and Wien's theory. Rayleigh gene and Wien's theory. Rayleigh gene and Wien's theory. Okay, this is a radial spectrum, and this them in nanometer, and this is unity watts per square meter per nanometer. And this experimentally observed graph. I'll draw it first. Kind of shape. This is experimentally observed, right? Okay. Then what's the Rayleigh gene? Actually, the Rayleigh gene and the Wien, they compose an equation to explain about shape, this shape of the gun. But they are failed. The Rayleigh gene failed to explain about for the low wavelength, and Wien fails to explain about high level. The Wien displacement, the Wien theory mismatch is this low part of this part. That's the low wavelength section of the graph. And Rayleigh gene's theory much close to that's high wavelength part of the graph, right? So first you write there first before we draw to this one. Just write there the Rayleigh gene theory and the Wien theory. Rayleigh gene theory and the Wien theory intelligence theory and the Wien theory are two theories that were introduced to explain the distribution of intensity of black body, distribution of intensities of black bodies. Okay, then right there. According to the Wien's theory, then the reparative right. According to the Wien's theory, the radiation intensity per wavelength, the radiation intensity per wavelength was given by the equation that's E lambda is equals to the C1 over lambda to the power of 5. You don't need to remember this, right? 1 over e to the lambda. So C2 over lambda t, right? C is a constant C2 over lambda. E to the power is C2 over lambda. Here you need to know that the lambda is the wavelength and C1 and C2 are constant. Right. Then, according to this equation, right, they plotted a graph. I will plot it before going to this thing. You can see when lambda goes to 0, when lambda goes to 0, let's see there. When this one goes to 0, this is infinite, this is go to 0, this is infinite. So what's happening? Lambda goes to 0. The intensity should goes to infinity, right? The intensity will not going to 0. So yeah. Yeah, I mean, then after you write this, when lambda goes to 0, plus a lambda where it's goes. That's okay. That goes to 0 also, right? Because here is lambda over c1 over lambda to the 5. Here e to the lambda c2 over lambda into e to the lambda over t, right? Lambda t. 3 over lambda. So here, when lambda goes to 0, this part goes to infinity. And then e to the infinity, that goes to infinity. So then the 1 over the infinity, it's got to 0. Before this function here, one lambda to the power 5 goes to 0, the rapid, this graph is rapid, then this goes to 0. So then e lambda goes to 0. It becomes little mathematics. Yeah. But when lambda goes to some particular value of the lambda, that's a lambda dash, lambda naught, let's say, then also this e lambda goes to 0. That before it's according to the practical observed graph, when lambda goes to infinity, let's say e lambda or the intensity should goes to I didn't see you that you left the thing. Now it's okay. I'm enabled or this, right?
කරන් ගිල්ලා අය
Sorry?
කරන්ට ගිල්ලා අය
Oh, hi. So here I'm where you left the meeting?
radiation intensity per wavelength was given by the equation.
The equation this one, right? This is the equation right there. That's E lambda equals C1 over lambda. So according to this equation, when lambda goes to 0, E lambda goes to 0. That's E lambda means the radiation energy emitted by the black body. Because this E to the part, the E to the power, this goes to infinity. So E to the infinity is infinity. So 1 over the infinity goes to 0. We don't care about this. When lambda goes to 0, this goes to infinity, you can see like that. But before this goes to infinity, this part is a rapid variation of this graph, then this goes to 0. That's why we consider. So when in this case, you can see, observe it this graph, then this part goes to 0 when lambda goes to infinity, 0. So that's why when lambda goes to 0, the complete function is goes to 0. So it's matched with the low wavelength. But the problem, when lambda goes to lambda naught or some particular value, then also the lambda goes to 0. But according to the practically observed graph, it should go to 0 when the lambda goes to infinity. But it's not happened. So that's why this Wien theory is failed to explain completely this graph. When the lambda goes to 0, that's lambda goes to a particular value. It's somewhere here, its intensity becomes 0. It's somewhere here. Let's say it's lambda naught. So according to the Wien theory, if we plot the graph, then we can get the graph similar to this. I will draw it with the different color, the red color one, right? It's overlap with the blue color one, mostly go like that. But in this case, it's also zero somewhere here, which is the graph obtained by the Wien's theory. Okay, first try this. So according to this, the Wien's theory failed to explain about the longer wavelength. So it's true for shorter wavelengths only. The longer wavelengths means it's just below the um, just below the red that's the visible lights, right? That's in the infrared region. So we call this contradiction is a infrared catastrophe. We call this an infrared catastrophe because it fails for longer wavelengths. So first to write this and then draw this red color line, add the red color line to your graph. Then alping adalandi karangin dahum maybe. This is experimental observed graph. This experimental data. So this. Okay. Then after write there. After that, right? And the Wien's theory. Wien's theory match with the experimental results. Match with the experimental results. Or experimental curve for shorter wavelengths only. So what shorter wavelengths only. So it's failed to explain the longer wavelength. It failed to explain the longer wavelength. Then it's called infrared catastrophe. And it's called infrared catastrophe. Catastrophe. Okay. Then right, according to the Rayleigh gene, the two names are Rayleigh gene. According to the Rayleigh genes theory, according to the radiation chain theory, the following equation, was given to explain the black body radiation, the black body spectrum. Explain the black body radiation spectrum. Then curve කියලා ලියන්නකො above curve. Right. So this equation now the මේ equation එකක්වත් මතක තියාගන්න ඕනේ නෙමෙයි මේ දෙකෙන්. මේවා ඔයගලන්ට නේ ඔයාලා මේ concept එක මොකක්ද කියලා මතක තියාගන්න ඉච්චරයි. මේකේ මොකක්ද කිව්වේ කියන එක තමයි. That's the in words you need to remember this what is explaining about this. That's according to this radiology theory. He given this that's the spectrum that intensity distribution as 2 pi ck T over lambda to the power 4. They given this this for this kind of equation. Here is the speed of light and k is the Boltzmann constant. Right. Okay. So this equation, according to this, you can see here, because it's directly the lambda to inversely proportional to this for the fourth power of the lambda. Now you can get it as when the lambda goes to 0, the C lambda goes to infinity. According to this equation, when lambda goes to infinity, the C lambda goes to 0. So it's valid for longer wavelengths only then. Right, according to that, the graph, according to this Rayleigh theory, this graph is matched with this part only. This part. Everything on no go man. That is make it. I mean experimental graph එක පොඩ්ඩක් බලන්න. අස් කරන්න වෙනවා මේ චුට්ටක් මෙහාට කරලා මේ. ඒකම ගත්ත මේකත් එක්කම යනවා හරි. වන්නේ මේ කුඩේ අඳින්න නැත්නම් මේක උඩම වගේ තමයි මේක එන්නේ හරි මේක හරියට මේකත් එක්ක මැච් වෙනවා. ඒතරමයි මේක this is මේ experimental graph එක මේක උඩම යන්නේ ඔහොම. local alien දෙකේ දෙවෙහුණා හරි. this is the religion theory. මේක වෙන plan. That is what the paper religion theory. Right. So this is fail for short wavelength. So it's called the ultraviolet catastrophe. You can draw this on there. Then right there, and this Rayleigh theory failed to explain. The Rayleigh theory failed to explain the shorter wavelength of the distribution, intensity distribution. Shorter wavelength of the intensity distribution. Can explain only the long wave, right? Okay, then this is fail. That's the Rayleigh and Wien they got to explain, but they couldn't explain it completely. Then the theory given by the Max Planck is more suitable with this. Right. I'll make it makana.
හරිද?
දැන් මෙච්චර දවස් කියන්නේ මේ මැස් ප්ලාන්ක්ස්ලා එනකම් ඉතර කල් හිටපු සයන්ටිස්ට්ලා හිතන් හිටියේ මේ they all think about that it vibrates වෙලා energy දෙන ඒවා තියෙන මේ vibration ඉඳන් දැන් මේ energy distribute වෙන black body එකේ surface එකෙන් තමයි මේ radiation emit වෙන්නේ. ඒතකොට මේ emit වෙන radiations වල තියෙන්නේ continuous energy. Any energy they can take. This is all the radiation they emitted, they can take any energy. කියලා තමයි ඒගොල්ලෝ හිතන්නේ. එහෙම හිතාගෙන මේවා මේ equation හදන්න ගිය හින්දා තමයි මේගොල්ලෝ fail වුනේ. හරි. So then Max Planck given the new concept that he told them these energies are corresponding to the that's atomic vibe that's vibrator on the surface atoms or vibrations in the තමයි but these atoms or these vibrators cannot take any energy. Any value of the energy they cannot take. They have in discrete values. So that there are energy levels. The one energy level particular to another like that. They are multiplication of some energy of a single smallest unit. And then the discrete energies are there. The Maxwell's given that is. These are energy levels are there. In between these two energy levels, so that energies are not available. The available energies are only the particular level, the discrete values. If we say that if energy is E, then next energy is 2E, and next one is 3E, like that. There are no energies in between this 1.5E, 1.2E, like that energy are not there. So that's he said this thing, and he derived the new equation to explain about this energy emitted by this radiation. So then it's completely matched with the experimentally observed black body, right? So this new one, that's the smallest unit of the energy corresponding to a radiation, is called the photons. So he introduced this new thing, and with the Einstein hypothesis also they match with this, and then this photon and also the quantum mechanical behavior of this light will come. So because they think that the light or radiation, they're having only the wave properties, and after this point, the people think that the light also, the wave is not a wave, it's can considered as a particle also. So they are having a particle nature. That thing is explained. The reason is because if it is a wave, the wave energy is proportional to the amplitude of the wave only. But if you consider of this as the particle, light as a particle, the particle energy, energy of the particle, it depends on the frequency also, right? So then he formulated the equation for this. That equation, you don't need to worry about the equations, but the theory part we'll discuss, right? Then right there, Planck's theory. We call it Planck hypothesis. So see, this experiment, given this as a hypothetically, but after it's a good approach to explain this experimental. So I just Planck's theory. Okay then. Right there, the Max Planck Planck presented Max Planck presented a hypothesis, the hypothesis known as the Planck hypothesis, known as the Planck hypothesis, to explain about the observed, experimentally observed black body spectrum. To explain about the experimentally observed black body spectrum. Okay, under that we write the Planck's hypothesis. Then write the first one. There are two board පොඩේ පේනවනේ ඇතිනේ මේ මෙහි කරන්ට් එක ගියා.
ඔව් අවුලන්නේ. දැන්
නෑ නේ ඔය විදිහට ඔය ගන්නට කරන්නේ. මේ route adapter එකේ තියෙන මේකට විතර router එකට විතර. Okay, first hypothesis you write there. The atoms of complete black body, the atoms of complete black body are oscillating. Atoms of complete black body are oscillating. An energy of these atomic oscillators, an energy of these atomic oscillators is given by the expression that E equals NHF. E equals NHF. Right? Yeah, N is called, that's N is the, it's called a quantum number. Call is a quantum number. Quantum number, this is a full number, right? This is 1, 2, 3, like number. And this H is a Planck constant. Planck constant. That's value is about 6.626 into 10 to the minus 34 2 seconds. And if it's the frequency of the radiation emitted, right? That's frequency of atomic oscillator, we can call it atomic oscillator also. Atomic oscillator. You can write this. This is the first hypothesis given. Give me a second. පල්ලයට කියලා ring light එක තිබ්බ එක පොතක් අරගෙන පොඩි පොතක්.
හරි.
ටිකක් පේනවනේ.
හවුද?
බලමු පැයකින් එයි තමයි. Right. Just then right there. According to the E equals NHF. According to the E equals NHF. The energy of an atom of a black body. Energy of an atom of the surface of the black body. Atom of the surface of the black body. Black body cannot have continuous values. Cannot have continuous values. So the energy is discrete. So the energy is discrete. Discrete. And it is called the energy is quantized. It is called energy is quantized. So all the value of the energies cannot taken in. They are having particular value of energies, discrete level of energies there. This is the first hypothesis, right? The second hypothesis you can write that this first one, this E equals NHF. That's the lowest energy then for the radiation emitted with the frequency F. Lowest energy is then N equals 1, that is HF. So then next level has 2 HF. Next level has 3 HF. That's a likewise, that's in chemistry you studied that they're having energy levels like around the, so one energy is there. So then the other part of that electrons or other thing are having in another energy level. Likewise, they are having discrete energy levels on it. Okay, second one, right? As long as atomic oscillator is in a specific energy level, as long as an atomic oscillator is in a specific energy level, there is no energy emission or absorption. There is no energy emission or absorption by it. No energy emission or absorption by it. Then simply say that if there's an energy level, this is energy level. When the atom or anything in lie in this energy level, they will not absorb or emit any energy. If they absorb energy, they goes to the higher level. If they emit the energy, they reduce, so they goes to lower energy, lower levels. So that's why, because this having a particular energy, they cannot be in a particular energy level only. If they absorb energy, they cannot be in that level. They have to go to another level, right? The right there, that is says that if you absorb some energy, the quantum level will increase. If decrease the energy, the quantum level will decrease. So quantum level go down. So then right there, when an atomic oscillator changes, its energy level, there is an emission or absorption of energy. When an atomic oscillator changes its energy level, there is an emission or absorption of energy. Then write the emission or absorption of energy by the atomic oscillator emission of absorption of energy by the atomic oscillators. Atomic oscillators are also in the form of energy quantum. Also in the form of energy quantum. It means when an atomic oscillator changes, changes its energy level into the adjacent level, energy level changes, oscillator changes its energy level into the adjacent energy levels, into adjacent energy level. The amount of energy it emits or absorbs, the amount of energy it emits or absorbs is HF. F is the frequency. Corresponding frequency, they're having a corresponding energy level. That's the level is HF. So that HF energy, we call it a photon, or energy of a photon, then we discuss. They write this energy quantum, this HF, this energy quantum or quanta, we call it this energy quanta. Quanta is the just the make up again. Plural quantum is singular word. This energy quantum, the HF is known as a photon. Known as a photon. So it's called a photon. So then we can say there's a light or any radiations are composed with this kind of photons. So packet of energies. So there are packet of energies. If the light hits on a surface, then this packet, some packets of energy will absorb, or some packets of energy will be emitted. Like that, right? So we can show it just like theoretically. Other models means actually you cannot see any level like this. It's the energy there, right? They're having a particular energy levels like this. Let's say this is n equals 0, n equals 1, n equals 2, n equals 3. Oh, I like this. Then their energy we can say this 0 and this side as HF energy, 2 HF, 3 HF, 4 HF, 5 HF. That's the goal like. If the transition is happen like let's say from this level to this energy level, they moves. If some atom is caused to the higher levels, they need to absorb the energy. Okay, then energy will absorb. That's absorbed energy is corresponding to these two levels. That is delta E equals 3 HF in this level minus HF in this level. So corresponding value is 2 HF. This much of energy needed to absorb to raise that atom is caused to the higher levels. With absorption, right? Another way, The other way we can say if one is come from this higher levels to the lower level, and then corresponding energy emitted. Emitted energy equals to the 5HF minus 4HF. That is H. Any quantum levels, if the atoms or molecules or anything is changes, the corresponding energy will absorb or emit. If we go from lower to higher levels, they absorb the energy. If we go from higher to lower levels, they emit the energy. So that's our emission. Emission of energy. And this is absorption. So remember this, we discussed under the laser parts, this absorption, the simulated emission. So these are energy levels there. So this kind of hypothetical nature having in there on the surface atom, and the energy levels are like this. Already Max Planck explained about this. This is a new theory. It's not existing theory in that era. If you finish the drawing, let me know. Right.
හරිද? Phoenix sir.
Okay. Then that's black body spectrum and its explanation using these theories are already finished, right? So the next observation regarding this quantum mechanical behaviors that are interactions between this wave and matter and radiation actually. Another phenomenon is a photoelectric effect. So let's see how we explain about this photoelectric effect. Right. So there's another different phenomena about this photoelectric effect, right? Okay, then write the topic as a photoelectric effect. photoelectric effect. Okay, this simple means this is that if we consider about the metal surface. Yeah, okay. So metal surface. When this electromagnetic radiation or any radiation, the radiation incident on the metal surface, right? Some the energy from this radiation can absorb by this metal, the surface atoms of the metals, and then they can eject the electron out. Some electrons they can eject. So this phenomena is called the photon. Here, the thing is then the particle when they hits on the particle, then particle can be ejected out. Up to this era, they observed that kind of interactions only. But here it's a new interaction they found. When this radiation wave are hit on the vapors, the electrons, so the matter are ejected or removing, right? So the this phenomenon is called that is a EM radiation, let's say, EM wave, and they're having some energy. So they absorb it and then some electrons are emitted. These emitted electrons are called the photoelectrons. Emitted electrons. Just observe this using this called if electroscope. අපි ඉස්සලාම එකේ ජාගම්කෝ ඉස්සලාම යන්න. When radiation or EM radiation incidents on a metal surface, incident on some metallic surfaces, energy sufficient window. We'll discuss this with the equation. When radiation incidents on some metallic surfaces, electrons are emitted by that surface. Electrons are emitted by that surface. And this phenomenon is known as photoelectric effects. Photoelectric effect. And it is first invented by or first observed by the scientist named Hertz. Hertz can be that was invented by Hertz. Scientist Hertz, right? And then also right, these emitted electrons, or these emitted electrons are called or are known as photoelectrons. 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 This photoelectron means that's the electrons emitted due to the radiation incident on the metal surface. You can draw this diagram. හරි. ඊපස්සේ මෙහෙම ලියන්න ඇතින් තරුවක් දාලා the photoelectric effect can be simply demonstrated. Photoelectric effect can be simply demonstrated with a negatively charged gold leaf electroscope. The negatively charged gold leaf electroscope. Right. Okay. Right. What is this called? If we know that's the electroscope. If you, I'll erase this one, right? Oh. The negatively charged electroscope. Electroscope is like, but that's a glass angle of there, and the gold leaf. It's a metal plate. Any metal plate you can place there, right? If you given a charge to them, so it will charge like this. Okay, negatively charged will given. Charges are distributed down the line like this. If given a negative charge is like that. Then what's happen? If that radiation are exposed to its metal plate, see, Then the radiations are emitted. Oh, that's incident on these metal plates. Some electrons are ejected out, right? Then what happened? When this electron is ejected out, because it's a negatively charged one, the negative charge on there this reduces. If the negative charge reduces, what happens? This separation or that's a deflection of this leaf, they contract, right? That's a deflection reduces. So it come like this. So some electrons are ejected out. Electrons reducing and then is deflection. That's a do like this. They come closer. You can see this. This angle is theta one and this angle is. You can remember the angle and the size checking and there. I mean, the guy is enough there. So this evidence on this. And then this photoelectric mode, we can more discuss. We can make a photo cell to demonstrate this photoelectric effects, right? Photo cell is that they are having a cathode, which can expose to the lights, and then anode is there. Then these electrons we can accelerate to run in a circuit, and then this running current, the photo current we call it, we can measure with the applied potential difference. So then we can observe and we can make equations to describe this phenomena, and then they're having theories related to this explanation. This observations we obtain using this phenomena. That's about according to this phenomena, and then we can discuss about the wave theory and particle theory related to this. Draw this and let me know.
What is it?
Then put a sign right there. The photoelectric effect can be explained. Photoelectric effect can be explained right. Right, the electric effect can be demonstrated by the photo cell, or photoelectric cell. So that is a photoelectric cell. We'll discuss about the photoelectric cell and all the things can cut into the that's all the things about the photoelectric effect we can explain this, right? Niranga. I'll draw it as like a spherical. You know, with one with the incidential form or a spherical way, you can draw it. This is the cathode. You can identify cathode is just like a C later, right? It's also called the concave cathode. Is there? Concave විදියට හදලා තියෙන ඉතල. එහා පැත්තට එන electrons emit කරන electrons ඒ පැත්ත මේ පැත්තට focus කරන්නේ lazy one. Anode. And then we can apply micrometer because small current will come that's to measure it. And also the voltmeter we measure to measure the voltage across the photo cell. Then we can apply external potential difference. The variable resistor we use. Then voltage we apply. Yeah. Right there to the second, right? Telling made a potential divide එකක්. So you can slide this key and then what is the potential difference you need to apply across this cathode and anode, you can apply. So voltage source. So this is right DC voltage. You can draw with me. Supply. And this cathode, this is evacuated glass envelope. No air inside. It's a vacuum. It's there, right? This glass envelope. This micrometer, this voltmeter. Already know this. This is a cathode. This anode. The radiations, but that's why the glass made with the transparent glass. The radiations are emitted, incident on this cathodes, right? Radiation come and incident on it. Then electrons are ejected out, and these electrons are moving like this, moves towards the anode. But the cathode is negatively charged, the anode is positively charged. Okay, විනාඩියක් ඉන්න. එන්ස්ට මාරු වෙන්න ඕනේ. කියන්නේ ඇත්තට මේක මේ පැත්තේ ප්‍රශ්නයක් නැහැ. මොකද මේක මේ අපි ප්‍රැක්ටිකල් එක කරද්දි දෙපැත්තටම ගන්න. හරි. කියන්නේ voltage වැඩි කරලා electron plus move කරන්නත් කාල් බලනවා අනිත් පැත්තට බලන්න වෙනවා. ඒක දෙපැත්තටම එහෙම පාවිච්චි කරන්න වෙනවා. You can draw this diagram. This is the photo cell. To apply like the potential is these emitted electrons can be now accelerate towards the anode and it make a current. So there's a photo current. Then you can draw the graph. That's the potential difference, applied potential difference versus the current, photo current. And then we can observe that if you increase the intensity of incident light, so this is the incident radiation or incident light. Incident light termination. මුල් කාලේ නම් ඔක UV light එකක් අරන් තමයි experiment එක කළේ. So intensity වැඩි කරාම they observe that the current increases. Photo current වැඩි. But if you change the intensity, that's the frequency of the incident light, right? That's frequency. That's the incident light has energy. Let's say HF. The particular photon energy of a photon is HF, right? So if particular frequencies, if you increase the frequency, the higher frequency, the electrons are emitted. But at a particular there's a frequency. There's a frequency. If the frequency below that value, no photoelectrons are emitted. They observed that. I will give that observation later. That's classical mechanics are failed to explain about those observations. That's the observations of this photoelectric effect or photocell experiment is much important there. You can first draw this one.
Arj-
Okay. Then right there, the negative terminal of the voltage supply, the terminal of the voltage supply is connected to the cathode, and the positive terminal to the anode, and the positive terminal to the anode. Then right, the region between the anode and cathode, cathode is vacuumed. Then it reduces the spreading of the electrons, emitted by the cathode, and hence and it minimizes the energy loss due to collision. Energy loss due to the collisions. Okay, then right. Wait, then right there. When the glass envelope is located in a dark place,